multivariate expected values. Recall that for discrete random variables, if x is a discrete random variable and we have a function g of x, then the expected value of g of x can be obtained by adding over all values of x the value of the function g of x times the probability of that value of x. In other words, the sum of g of x times f of x. F of x is the probability function. Suppose we have a function of two or more random variables, x and y. Call that function g of x of y. Then the expected value is defined in exactly the same fashion. The expected value of g of x, y is obtained by adding over all pairs of values, x and y, the value of the function, g of x, y, times the probability of that pair. And remember, the probability of a given pair is the definition of the probability function, f of x, y. So this becomes the sum over all values of x and y, g of x of y, f of x, y. Here's an example. Suppose the joint probability function of two random variables is given in the table below. Suppose you're asked to find the expected value of x times y. In this case, the function g of x, y is x times y. We can go through the 8 values in this table, 8 probabilities in this table, and in each case multiply by the corresponding value of the function and add. And when we do that, you'll notice that for the first row of the table, y is equal to 0, and so x times y is equal to 0. For that reason, below you see things like 0 times 1/8 plus 0 times 2/8 plus 0 times 1/8 plus 0 times 0. In fact, there are only 3 non-zero values corresponding to the last 3 cells. 1 times 1/8 plus 2 times 2/8 plus 3 times 1/8. And this simplifies to 8 over 8, or 1. E of x times y is equal to 1. Properties of multivariate expected values. Recall the very important linearity property of expected value for one random variable. If I define a new random variable by a times g of x plus b, where a and b are constants, then its expected value is a times the expected value of g of x plus b. This basically asserts that expectation is a linear operator. And we have exactly the same property for multivariate expected values. For example, if I have two functions, g1 and g2, and two constants, a and b, and I'm interested in the expected value of a times g1 of xy plus b times g2 of xy. That's simply a times the expected value of g1 plus b times the expected value of g2. Is the expected value of a product always equal to the product of the expected values? Is the average of a product always equal to the product of the averages? This example is motivated by a fictitious parallel universe in which a prairie province is governed by a probability course dropout, who is enlightened in at least one respect. He decides that the fitter couples who apply for homesteads in his province should get larger homesteads than those that are less fit. And so happy couples like those depicted here slog across the country and arrive at the boundary of his province. He has already discovered that the average walking speed of men, like the man in this picture, is, over prairie terrain, 3 kilometers an hour. The average for women, 2 kilometers an hour. And you might wonder why that's the case. It's, of course, because the woman ended up carrying all of the gear, including the child. The scheme is this. They begin at one corner of their homestead, labeled start in this figure. The man walks for an hour, a distance x. The woman also walks for an hour, a distance y, perpendicular to the man. At the end of that hour, a gun goes off, and they freeze in place. And those locations determine the two corners of their homestead. A clever idea, because the fittest couples, the Olympians, will end up with larger homesteads than the chip-loving, couch-confined couples who would rather stop and have lunch immediately after the gun goes off. So obviously the governor is assuming that the average homestead is 6 square kilometers in size. Question is that likely to be the case? The area of the homestead is, of course, x times y. So the question is the expected value of x times y equal to e of x times e of y? Or is the expected value of a product equal to the product of the expected values? We'll show a little later that this is, in fact, true if x and y are independent of each other. But otherwise, they may differ, and they may differ by quite a lot. In fact, the difference between the expected value of the product and the product of the expectations is called the covariance between x and y. What about the difference in this example? Is it likely to be positive or negative? What's the cause of the difference, for example? Think about three possible scenarios. The first is that the homesteading woman picks her spouse purely at random, without regard to any characteristics, including his speed on a prairie track. In this case, the expected value of x times y is e of x times e of y. The covariance is 0 because x and y are independent of one another. Of course, the homesteading woman calls the shots, there being no shortage of them. Let's suppose she's rather keen on racing across the prairie and chooses a spouse that's similar. Olympian chooses Olympian. Large values of y will be associated with large values of x. In this case, you can imagine extremely large homesteads, extremely large products of x times y, much bigger than e of x times e of y, and of course some that would be very small. The non-Olympians, the couch potatoes, would choose cohabitation with another couch potato. They can share couch and potato. That's the likes attract scenario. But there's another possibility, and that's opposites attract. Couch potato woman chooses Olympian spouse. Olympian woman prefers couch potato spouse. In each case, someone to complement their deficiencies. Here, the expected value of x times y is likely to be smaller than e of x times e of y. Indeed, a true couch potato might travel at 0 kilometers an hour, in which case e of x times y would be 0, because one or other of the two would inevitably be 0. So it's possible for covariance to be 0, or positive, or negative, depending on those three scenarios: independent, likes attract, or opposites attract. I suspect in this example, it's the likes attract scenario that would prevail, and in fact, the governor would run out of homesteads much more quickly than he expected. He should have completed this course. Here's an example. Suppose the joint probability function of x and y is 2x plus y over 30 when x is 1 or 2 and y is 1, 2, 3. The probability function is given in the table below. The question is, in this case, is it true that e of xy is equal to e of x times e of y? Solution. Well, we have little choice but to compute all three, exy, ex, and ey. And to that end, it's helpful to have the marginal probability functions for both x and y, which are listed here in the margins of the table. From those marginal probability functions, we can determine the expected value of x, 48 over 30, and the expected value of y, which is 64 over 30. We obtain the expected value of x times y by running through the 6 possible values for that product, multiplying each by the corresponding probabilities given in the probability function table, and adding them up. And when we do that, we end up with 17 over 5, which, although it's close, is not exactly equal to 48 over 30 times 64 over 30. Therefore, in this case, the covariance is not 0. The expected value of x times y is not equal to e of x times e of y. I said earlier that the covariance is 0 if the two random variables are independent of one another. Remember what that means. That means that the joint probability function factors into a part corresponding to x, fx of x, and the marginal distribution of y, fy of y. In this case, if x and y are independent random variables, then the expected value of x times y is e of x times e of y. The proof is quite simple. Evaluate the expected value of x times y. It's the sum over all pairs, all possible x, y, the product x times y times f of x, y. And of course, the sum over all pairs means the sum over all x and the sum over all y. But you'll notice that when I'm adding over all possible y's, I'm holding x fixed. I can remove the term involving x outside the summation sign for y. When I do that, I end up with essentially the product of two sums, 1 over all x, x times f of x, 1 over all y, y times f of y. Of course, the second is the expected value of y, the first the expected value of x. So we end up with the product e of y times e of x. The converse to this statement would state that if e of xy was e of x times e of y, then they would be independent. But that statement is false. It is in fact possible for two random variables to satisfy the condition that the expected value of the product is the product of the expected values, but nevertheless, those two random variables x and y are dependent. They're not independent, and we'll show a simple example of that in a little while.